Welcome back, guys. We've got another video of doing double integrals in polar coordinates. So in this one, it's a show that question. So we want to show that this double integral is equal to 2 over 15 times 25 minus root 5. And the region that we're integrating over is this slightly complicated looking region here. So it satisfies that x squared plus y squared has to be greater than or equal to 1, but less than or equal to 5. And y has to be greater than or equal to a half x and less than or equal to 2x. So the first thing that we should always do when we do any double integral, regardless of whether it's in polar coordinates or not, is draw the region R, draw the region that we're integrating over. So let's do that right now. So as you can see here, I have drawn a few different shapes and stuff, and this is going to make up the region. So first of all, let me just explain what I've done here. So I've drawn two circles, as you can see. The small circle has equation x squared plus y squared equals 1, and the bigger circle has the equation x squared plus y squared equals 5. That's because these are the lower and upper bounds, respectively, of what x squared plus y squared can be. So we know that we're looking at least for values of x and y that are inside of this donut or annulus shape, okay? So inside of the donut is where we're looking, at least. And then we've got this extra condition here that y has to be greater than or equal to a half x, but less than or equal to 2x. So what's going on there? Well, I've drawn the function y equals a half x, and I've also drawn y equals 2x. As you can see here, these are the straight lines. And so what we're looking for are the y coordinates that are, or the values such that the y coordinates are greater than or equal to a half x, but less than or equal to 2x. So we need to be above the y equals a half x function, but below the y equals 2x function. And both of these conditions need to be satisfied at the same time. So what we are looking for is to integrate over this region here, if this makes sense. Okay, because this is the only region in the graph, in the diagram, where both conditions are satisfied. So the x and y coordinates have the property that x squared plus y squared is between 1 and 5, and the y coordinates are bigger than or equal to half the x coordinates, but less than or equal to 2 times the x coordinates. Okay, so hopefully that makes sense. This is not the area that we're trying to look for, but rather the region that we're actually integrating the function x plus y over. Now, I've not said anything about polar coordinates yet. The reason why we want to do this in polar coordinates is very simple. It's just because the region that we're integrating over has a circular vibe to it, a radial kind of situation going on. You might imagine trying to find the x and y limits here, trying to keep this in Cartesian. It looks like it would be a total nightmare. But in polar, it's nice and easy. So let's just go straight ahead and convert it into polar right now. So we're going to do our double integral, and the function is x plus y. Now remember, x in polar coordinates is r cos theta, and y in polar coordinates is r sine theta. Okay, and I'm going to put that in brackets. And remember, guys, dx dy, when you convert into polar coordinates, becomes r dr d theta. Okay, that's always going to happen. That's just how it works. Okay, that's because of something called the Jacobian. So when you convert from dx dy into polar coordinates, it becomes r dr d theta. Lovely. Okay, so the inside integral, the rightmost integral, these are going to have r limits. So the lowest r value is 1 and the biggest is root 5. Because we are looking at values of r, remember r is simply the distance from each point from the origin. So we're looking at values of r between 1 and the square root of 5. And this time the theta values, because in the previous videos we've done on this, the theta values have just been 0 and 2 pi because we've gone all the way around the region. This time that's not the case. So this time it's actually not as obvious what the angles are. Like, what even are they? So what I'm going to do for now, and you'll see why this is useful, particularly in this question right now, is I'm going to do some labels. I'm going to say that this angle right here is alpha, and this angle here, all of it, is beta, okay? Now, we can work out what they are, but you will see that it's better to leave them like that for now, okay? And we will work out what they actually are in a very short amount of time. So the lower limit is going to be alpha and the upper one is going to be beta, because those are the angles going anti-clockwise from the positive x-axis. So that's what those are. Lovely. And then we can actually go in and we can at least do the inside integral. So we've got the integral from alpha to beta of the integral from 1 to root 5. I'm just going to expand out the r's here, guys. So I've got r squared cos theta plus r squared sine theta, dr d theta. And now we can actually integrate these this stuff here. So this is equal to, put some equal signs in, integral from alpha to beta, and then we can integrate. So what I'm probably going to do is actually think about the r being factorized out. I think that's probably better. So imagine that the r has been, or the r squared has been factorized out. We've got cos theta plus sine theta times r squared. So overall, that's going to be 1/3 cos theta plus sine theta times r cubed. Okay, hopefully that makes sense the way that I've done that. I've factored the r squared out. Okay, and our limits are 1 and the square root of 5. Put a d theta there. Okay, and of course we just keep doing our working out. This part is easy. The alpha and beta stuff is where it's going to get a little bit trickier. So we're plugging our values in. So we've got 1/3 cos theta. Remember, we're plugging into r sine theta. Close bracket. Now, guys, the square root of 5 cubed means the square root of 5 times the square root of 5, which is 5, times the square root of 5 one more time. So it's 5 root 5. So times 5 root 5 there. Okay, and then we're going to subtract the same thing, but with 1. So it's going to be nice and easy. It's just going to be 1/3, open bracket, cos theta plus sine theta times just 1 cubed. Okay, so that's literally all there is to it. I think there's one more bracket that goes there. Cool. And then d theta. So now we can potentially try and factor some constant stuff out of this, because at the moment it's a bit messy to actually try and integrate. So I'm going to rewrite this as the integral from alpha to beta, and then I can see here that I've got cos theta plus sine theta, so I can just do that in brackets now. So cos theta plus sine theta like that, close bracket. And then you can see for the first term I've got basically 5 root 5 over 3, so 5 root 5 over 3, and then this term here I've got minus 1/3, so I've just factorized that. And the reason I've done this is so that I can just take it out. So I'm just going to go 5 root 5 over 3 minus 1/3, close bracket, and then I'm going to do my integral from alpha to beta of cos theta plus sine theta. This is just a personal preference for me. I just think it's a bit nicer. There we go. Okay, cool. Now we can actually integrate the function. So we have got, this is equal to 5 root 5 over 3 minus 1/3, and then square brackets, and we integrate cos theta and sine theta. So cos integrates to sine, and sine integrates to minus cos. Okay, so we've got sine theta minus cos theta. And just to sanity check that, remember sine differentiates to cos and cos differentiates to minus sine. So minus cos would differentiate to positive sine. And this is from alpha up to beta. And remember, we've still not actually worked out what these are. So at this point, now we can actually start thinking about what alpha and beta should be. So the reason why I didn't want to work out alpha and beta earlier is because the most obvious way of doing it is actually to get alpha and beta in terms of inverse tan, which is no good, because then we'd be doing sine of inverse tan, and that's just a mess. Let me show you what I mean by this. So let's look at alpha first, right? I can definitely draw a triangle to find what alpha is. It's not difficult. It's just kind of basic trigonometry, SOHCAHTOA. Here's a right angle triangle. This is the, remember, this is the function y equals a half x. That quite literally means that when we go horizontally along by 2, we're only going up by 1. So I can draw this triangle to just be 2 on the base and 1 on the height. In fact, it could be anything. It could be 2k and 1k if I want. It doesn't matter for any constant. As long as the base is double the height, then this is fine. It's going to be the same angle. But just to keep it nice and simple, 2 and 1 look pretty good. And then this is the angle alpha. So you can clearly see that our first instinct might be, well, let's just realize that in this case, alpha is just inverse tan of 1 over 2, right? Because it's opposite over adjacent. But the problem is that this is not very helpful because remember, we need to do like sine of that, sine of alpha, sine of inverse tan of a half. That's just gross. So really what I want is to find alpha in terms of sine and also in terms of cos, because actually if I go back again, you will see that I need to do sine of alpha and cos of alpha, and I need to do sine of beta and cos of beta as well. So really I need to work out what sine of alpha, cos of alpha, sine of beta, and cos of beta all are. I don't care about this in terms of tan. It's just a waste of time. So that's why we didn't do it originally, because it's not obvious that that would be the case. So let's just write some stuff down. So on this triangle, we can see that sine alpha, remember, sine is opposite over hypotenuse. So we need to work out what the hypotenuse is. Luckily, it's nice and simple. It's just going to be the square root of 5 here because, first of all, because it's just Pythagoras. But guys, second of all, it's just like this. This is the triangle, right? So we're along by 1, we go up by, oh, sorry, we go along by 2, we go up by 1. That's on there. That's where it intersects the circle. And then, of course, that's going to be the square root of 5. So if you want to think about it like that, then, of course, you can. It's not the best way. Pythagoras is the simplest way to think about this. And of course, we can see that that would mean sine, because it is opposite over hypotenuse. We can see that we've got 1 over the square root of 5 for sine alpha. Cos alpha is pretty simple as well, because it's just 2 over root 5, okay, because that is adjacent over hypotenuse. Cool. Now, let's go and do beta, okay? So we don't even necessarily care what alpha and beta actually are. We only care about what cos of alpha and beta actually are. So here's another triangle. Maybe I should actually draw it a bit steeper just to differentiate what they look like. Remember, this one is a bit taller and not as wide. The important thing here is that actually these two triangles are similar to each other because this angle here is beta here. But this time, because remember, this is the function y equals 2x, that means that as you go along by 1, you go up by 2. So the base is 1 and the height is 2. And you can actually see, because we've got side, angle, side, the triangles are literally the same. And like technically up here, this would be alpha. So it might not come as a surprise that what we'll have for this one is that sine of beta and sine of alpha just swap places, okay? So sine of beta, let's do that one first. This is still going to be root 5 because it's the same triangle. Sine of beta is just going to be 2 over root 5. And cos of beta is just going to be 1 over root 5, okay? Lovely. Now, again, just to be very clear why we've done this, it's because we need to plug it all in. So this is going to be equal to 5 root 5 over 3 minus a third, and then plugging in. So big bracket, sine of beta. Sine of beta, what did we say sine of beta was? It's 2 over root 5. So let's go, and do you know what? Just to show the algebra, I will actually write this out like this first. So put a bracket there, being very careful of all the brackets here. So that's sine of beta minus, and we've got sine of alpha minus cos of alpha, close bracket, and I think maybe there's one more close bracket there. Cool. So we've got 5 root 5 over 3 minus 1 over 3. And then we can plug stuff in. So sine of beta, again, sine of beta is 2 over root 5. Okay, so 2 over root 5 goes here. Cos of beta was 1 over root 5. And then sine of alpha, we said that that was 1 over root 5. So minus 1 over root 5. And cos of alpha was 2 over root 5. And there's a minus minus here, so it becomes plus 2 over root 5, like that, close bracket. Cool. Remember, what we're trying to get to here, guys, is we are trying to show that this whole thing is 2 over 15 times 25 minus root 5. Just remember, that's what we're trying to get to, okay? It looks pretty good, though, because a lot of stuff is going to kind of simplify and cancel out in some nice ways. So we've got 5 root 5 over 3 minus a third. We'll deal with that in a second. And then here you can see that we've got 2 over root 5 plus another 2 over root 5. That's 4 over root 5. And then minus 1 over root 5 minus another. So overall, this whole thing is just 2 over root 5. Okay, cool. And then we can kind of expand this out a little bit. So the first bracket gives us 10 over 3 because the root 5s cancel out. So I'm just doing 5 root 5 over 3 times 2 over root 5. So the root 5s cancel, and it simplifies to just being 5 times 2 over 3, so 10 over 3. And then minus, this is 2 over 3 root 5. Remember that we're trying to get to a point where this has got a 2 over 15 on the outside. So now we should definitely be taking that to the outside. So this needs to be rewritten as 2 over 15, open bracket. Let's work out what actually needs to go here. So if you put a 25 here, what you can see is you do 2 over 15 times 25. That's 50 over 15. And that is going to simplify to 10 over 3. So 25 is the number that should go here. And then we're doing minus, and then we've got to work out what goes here instead of 2 over 3 root 5. So the way that you can do that is you can just go 2 over 3 root 5 divided by 2 over 15. You can either do that on a calculator, or you can do that in your, in your head, or I guess you could just write it down. But you do end up getting overall that simplifies to just the square root of 5 like that. And that is the answer. So it's 2 over 15 times 25 minus the square root of 5, which is what we were trying to show. So there is all the working out, guys. I will zoom out so you can see everything that we did. Hopefully that's still big enough. That's going to be very, very small on your screen. I'm sure of it. But that's what we did. So we drew the region, we basically just we converted it to double integrals, we computed it, and then the tough bit was working out exactly what alpha and beta were. But we did that using just some basic trigonometry in the end of it. And of course, we end up getting to the answer. So as always, guys, I do appreciate you guys watching all the way to the end. It is very, very useful for me and helps the video do really well. So I appreciate that so much. And of course, I hope that it helped you do very well in understanding how to do a double integral in polar coordinates. As always, thank you for watching, and I'll see you in the next one. Cheers.